Experiment 14 is another experiment on kinetics and using that to determine reaction orders and rate constants. But rather than in experiment 13, where we actually use the method of initial rates to determine that information, we're going to be taking experimental data and graphing it to determine reaction order, and then using a lot of the same methods that we've already used to determine rate constants. So this chemical equation here is what we have data for. And with any chemical equation, we can write a generic rate law by saying rate equals rate constant times the concentration of each reactant raised to powers that are reaction orders. And again, we cannot use a chemical equation to directly provide those reaction orders. We need to use experimental data. So again, to contrast what you did in experiment 13, we did the method of initial rates as a mechanism for determining reaction orders. In this lab, we're going to provide you data where you will be able to use Microsoft Excel and an analysis of that data in a different way than we use the method of initial rates to determine reaction order. So 2 sets of experimental data, and like we have with the method of initial rates, you're going to be holding one set of concentrations constant while you manipulate the others and you look at how the reaction rate changes. So looking at our generic rate law here, if we were to hold oxygen concentration constant, so what we would have here is essentially 2 constants in this rate law. So this rate constant obviously is constant, but if we're not changing the oxygen concentration, we can lump that together with this rate constant and create a new rate constant. Let's just call it K prime and rewrite our rate law here. Rate equals rate constant times the concentration of NO to the power X. We're going to use experiment 1 data to determine what the value of X is, what the reaction order is, by determining what this data looks like when we plot it in 3 different ways. We're going to do the same thing then with holding NO constant. So again, holding NO constant allows us to merge these guys together as a new constant. We're going to call that one K double prime. So we can rewrite our rate law now as rate equals our rate constant now is K double prime times the concentration of oxygen raised to the power that is Y. We're going to use data from experiment 2 to help determine the value of Y. So we still are going to be using experimental data to determine reaction orders, but it's a different way than we learned how to do with experiment 13 and the method of initial rates. All right, so what are you going to do with this? And again, I highly encourage you, make sure to watch Dr. Brown's video. He does a great job of walking through how to analyze this data using Microsoft Excel. My video here is more just on the theory and the background for how this is going to work. So what we're going to do with experiment 1 data is we're basically holding oxygen concentration constant, and then we're looking at how the concentration of NO changes, and we see resultant changes in reaction rate. So what we're going to do is plot 3 different things as a function of time. So time is always going to be on our x-axis, but we're going to have one plot where we look at the concentration of NO directly, and then we're going to have the ln of the concentration of NO, so the natural log of the NO concentration, or inverse NO concentration, 1 over. So you need to create these data sets and then learn how to plot them as scatter plots in Microsoft Excel and see which of these data show you a straight line. When you get data that shows you a straight line, that is going to tell you that that is the reaction order. Do you remember when we have these 3 different flavors of equations that we can use for 0, 1st, or 2nd order processes, right? So what we can have here is when we plot these or put these equations in these forms, we basically see that they take on the form of a y equals mx plus b, or a straight line. So when we have a certain reaction that fits a straight line, when we've plotted 1 over NO concentration versus time, we can see that that is going to be this flavor of an equation, right? So our x is going to be our time there. Our y variable is some way of analyzing a change in concentration of our species there. And what we're going to see here is that we will just be able to use whichever plot gives us a straight line to tell us reaction order. So the fact that the shape of a plot of 1 over gives us a straight line tells us that we are second order with respect to NO. So that tells us that x is going to be equal to a 2 there. And also one other piece of information that's important to get from this plot is the slope of the plot will give us the rate constant, that merged together rate constant, which we called K prime here. So after you've plotted this data and looked at 3 different plots and determined which one gives you the straight line, that will tell you the reaction order, and then the slope is an important piece of information that tells us that merged together rate constant, K prime. Okay, so I'm going to go a little bit more quickly now because the second half of this paper here walks through how we do that for the second set of experimental data. So the second set of experimental data is now where we're holding NO constant. So that's going to be looking at changes in oxygen concentration as a function of time. And again, we're asking the question, which one of these is linear? When we see here, if we plot the natural log of the oxygen concentration as a function of time, and that's what gives a straight line, that tells us that this reaction is first order, right? So first order with respect to O2. So again, we can put this in, and now we know that y is going to be equal to 1 because it is first order. And other piece of information that's going to be important to get from this line is the slope, because that is going to be this merged together rate constant, which we called K double prime. All right, so after you've done that graphing data on Excel, 2 pieces of information we're going to need to have, K prime and K double prime. We get the reaction orders from picking which plot was a linear plot, and then we need to know those rate constants. We need to know the slopes of those 2 linear plots. All right, so what do we do with all of this now? Okay. Oh, this is just a figure or a picture here that kind of shows all of that together. So if you wanted to pause for a second and kind of take a look at any of this, this has all of this information together. All right, so now what do we do with all of this information? So to summarize, from experiment 1, we now know that the reaction is second order with respect to NO because a plot of 1 over NO versus time gave us a linear plot. The slope from that plot is going to give us K prime. Okay, go to experiment 2 data. Now we plot ln of the oxygen concentration, and that's what's going to give us a linear plot. So that told us it was first order with respect to O2. So that rate law looks like this. Rate equals rate constant times O2 to the first power, first order. Again, the slope is going to give us that K double prime number. All right, so what do we do with these? Because at the end of the day, we really want the rate constant for our full experiment, our full rate law, right? Well, I'm going to talk about this as being our decombining of constants. Remember that we created these K primes and K double primes by merging the K with a concentration that we were keeping constant. So now we're going to just deconvolute that. We're going to break it apart. So recalling here, remember when we made this new constant K prime, right? It's because we merged these guys together. Well, now that we know what K prime is and we know what we set K prime equal to, and we know what that concentration was, and now we know what that Y is, all of a sudden the only variable that's left is K. That was a lot there, so let me go through it again if it was unclear. When we made this new constant K prime, we made it by merging together 2 things that we knew were constant. The K that we're interested in for our overall rate law. And then since we were holding the concentration of oxygen constant, we sort of merged it together. Well, now we know lots of pieces of information. Even though we held this constant, so we sort of merged it together, we know what that number is. And we used the plot of our straight line to tell us what Y was. We learned that it was second order here. And we know what the slope of that linear line was. That was our K prime. So now that we have all of these pieces of information, the only thing that's unknown here is our K value. So we sort of break this back apart to get our value of K. All right, a little bit more quickly, I'm just going to go same thing on the other side, right? We merged things together here to create our new constant K double prime. So these things got merged together. We said that they were equal to this. So now that we know what our rate constant K double prime is, from the slope of our plot. We know what x is equal to 1 because of what we plotted to get a straight line, and we know what we held that NO concentration to when we kept it constant. We can solve now for K. So now we have rate constants that we got from each of these sets of experimental data. The last thing to do is to say, well, there's always potentially some experimental error, so let's average these guys together. So the last piece is saying, you know what, let's average these guys together, and then when we put it all back together, now we can get our full rate law that has the rate constant as well as the reaction orders for both NO and O2. I know that was a lot, but hopefully it all made sense.